Yes, I am a bit of an expert at these things.
Okay, thank you, Daddy Pig. So this is a walkthrough of what you need to do to be able to be successful on exam 3. So your exam will be the same format as always. So first part, true or false, really general organic knowledge questions. First one deals with carboxylic acid derivatives. That's all of chapter 21, so that term has a very specific definition. You should know that. Part 2, a recurring theme will be, of the multiple functional groups that we're talking about, you have to precisely know the IUPAC naming. So this functional group is a nitrile. Nitriles are named as alkane nitriles. The reason why this is false is that we're missing an E between those two ends. Question 3 talks about early or late transition states. This is important because in chapter 21 for nucleophilic acyl substitution we have bad leaving groups being expelled. And in chapter 1 it tells you that bad leaving groups can be expelled if they are expelled in an exothermic step. So that relates to Hammond's postulate. Next question is just a functional group interconversion. So you cannot oxidize acid chlorides to give aldehydes. Next question is a relative reactivity question. Chapter 21 is just full of nucleophilic acyl substitution. Of those carboxylic acid derivatives that we talked about, there is a ranking, a relative reactivity sequence. Goes acid halides, anhydrides, then esters. So that makes this false. Next question is just a functional group conversion question. Obviously this is incorrect. Next question deals with the mechanism of nucleophilic acyl substitution. The important thing here is that mechanism is not a one-step process. It's at least a two-step process. It's an addition-elimination mechanism. Question 8, oxidative cleavage of hex 3-ine produces ethanoic acid is false. Oxidative cleavage of alkynes can give carboxylic acids, but the position of the triple bond in this isomer would not give you the 2-carbon ethanoic acid. Amongst all the functional groups we talked about, we also talked about some cyclic variations. We talked about lactones and lactams. Lactams are the cyclic amides. And then question 10 lastly, another question dealing with functional groups, more precisely structure of functional groups, and this is just talking about the number of oxygens in both of those functional groups. They both have 3. To carry on the theme, questions 11 to 13 are just testing your ability to identify functional groups. Gets kind of tricky now because there's a bunch of functional groups now with oxygens or multiple oxygens, especially ones with CO double bonds, but attention to the detail of the structures will get you to the correct functional group. Pretty much guarantee there'll be a question on acid strength. Acid strength has to do with how good or willing is your species to give up a proton. That is controlled by the stability of the conjugate base. Anything that makes that conjugate base more stable is going to give rise to a more acidic species. So you evaluate the anions produced when the most acidic hydrogen is removed, and then the one that gives you the most stable anion is going to come from the strongest acid. So this will give you negative charge on oxygen, this will give you negative charge on oxygen, this will give you negative charge on oxygen, but stabilized through resonance, so this is the most acidic. Here we're addressing the effect of electron withdrawing groups on the same functional group of a carboxylic acid. Stronger electron withdrawing groups give you stronger acids, more electron withdrawing groups give you stronger acids, and electron withdrawing groups closer to your acid give you stronger acids. Combination of those things make this the most acidic. Here it's a similar type of question, but it's important to note we're dealing with different functional groups. Here's an aldehyde, this is an anhydride, this is a carboxylic acid. This is the only one that has a protic hydrogen. Doesn't matter about these substituents. These hydrogens are not acidic, so this is the most acidic. Of course, there'll be our UPAC questions. Again, this all starts with having an understanding of functional group. The functional group here is an amide. So you're going to name this as an amide. The rules say you look to see how many carbons are in the carbon of your CO chain. 1, so this is some methanamide. We have substituents on the nitrogen. We have 2 methyls. Obviously they're both connected to nitrogen, so this is the NN dimethyl methanamide. Here we have an anhydride. Anhydrides are named as alkanoic anhydrides. Here we have a 3-carbon sequence that comes from propanoic acid. Here we have a 5-carbon sequence coming from pentanoic acid. The rules for anhydrides say you list the higher priority substituent first. So this is not because of making it alphabetical, it's because pentanoic has a higher priority than propanoic, and that's priority like we did for chirality, like we did for assigning Z and E. So highest priority first, second priority second. The reverse issue in this question, you're given the name, you have to draw the structure. So the ending OATE tells you it's an ester. It's an ethyl ester, which means you've got a 2-carbon sequence connected to the oxygen. It's the ethyl ester of the butane, so that's a 4-carbon carboxylic acid. So it's not ethyl, so this goes on the left, this goes on the right. The first part of the name is the alcohol derived part. The second part of the name is your carboxylic acid derived part. Those 4 and 2 carbon sequences are not interchangeable. Next one, this propanol fluoride tells you it's an acid fluoride. So you've got a fluorine connected to your CO double bond. The propan part tells you it's a 3-carbon derived sequence. So here's our 1, 2, 3, and it's the 2-methyl. So carbon number 1 is established by the carbon of the CO double bond. So that makes this 1, 2, 3. This is carbon 2. So that's where your methyl substituent would be for 2-methyl propanoyl fluoride. Of course, reagent and starting material product. Again, this is all based on starting material, reagents, product. So if we start here, we have an aromatic ring and a carboxylic acid. We're going from carboxylic acid to primary alcohol. So that's a reduction. You look in your chart, you see this is the reducing agent. Then our next 2 questions involve this as our product. When we see the reagents of magnesium followed by CO2 followed by acid, that should help you identify that this is going to be a Grignard type reaction. A Grignard reaction where your Grignard reacts with CO2 and acid to give a carboxylic acid. So the carbon of this CO2 is going to become this carbon. So this protocol adds a carbon, in fact adds a CO2H into your start material, so your starting material must have 1 carbon less. Right, so this has 8 carbons total. We're providing 1, so our start material needs to have 7. So the CBr bond is where the magnesium inserts to form your Grignard. That does a nucleophilic attack on your carbon dioxide. Protonation gives you the neutral carboxylic acid. Here we also have another method of making carboxylic acid involving the hydrolysis of a nitrile. The nitrile is made using cyanide as a nucleophile to displace this leaving group. That gives you the nitrile that's then hydrolyzed to the carboxylic acid. Again, the carbon of the cyanide is the carbon of your carboxylic acid. So 8 carbon product, here's 1 carbon, so 7 carbons in our starting material. Obvious question here. Chapter 21 is just full of nucleophilic acyl substitution. Here we have one such example. Nucleophilic acyl substitution is always the same. Nucleophile attacks the carbon, pushes the pi electrons onto the oxygen. That produces your tetrahedral intermediate that then in a second step expels your leaving group. In this case, deprotonation gets us to our neutral product. So addition-elimination mechanism proceeding through a tetrahedral intermediate. That is classic nucleophilic acyl substitution. Next question, again relating to functional groups. 2 relatively popular molecules. Here we have the ester linkages that are characteristic of heroin. Morphine is really just the alcohol version of the same basic structure. So which hydrogen is most acidic? You're all experts in acid strength by now. It's going to be one of the OHs, because negative charge on oxygen is going to be better than negative charge on carbon. Negative charge on this oxygen is going to be resonance stabilized by the ring. This is very similar to why phenol, for example, is more acidic, a better proton donor than cyclohexanol. Next is the reagent question. Morphine to heroin is really just converting an alcohol to an ester. So there are several different ways that you can do that. Classic way would be to use, in this case we're making our 2 carbon ester, so we'd need a 2 carbon acid chloride or carboxylic acid or anhydride. All of those equally correct. Going back from heroin to morphine is just converting an ester to an alcohol. You can do this either using water, so that would then just be your hydrolysis. If you use any of these other nucleophiles, you would also then take off your carbonyl group, leaving behind the OH. Another reagent-based question, again, testing your understanding or connection of functional group, starter material, reagent, product. So carboxylic acid to amide, reagent is an amine plus heat. Carboxylic acid to its deprotonated form, the answer really is any base that will deprotonate your acid. Last question is mild oxidizing agent to make carboxylic acid. Here, because we're using the mild oxidizing agent, the answer is aldehyde. So chapter 20-21 is really just about carboxylic acids and carboxylic acid derivatives.